So now we're saying we have a mysterious aromatic compound, like smiley face or whatsoever, that contains elements, carbon, hydrogen, and some kind of halogen. So X just states for some kind of halogen. Now, on top of the spectroscopy information, this sentence actually gives you lots of information in it. First of all, we're saying this compound is aromatic, right? So when we're talking about aromatic, we're saying, hey, this molecule must have some kind of ring structure in it, must have some kind of pi bonds, right? Or the other way to put it is our degree of unsaturation is at least 2. Right, you at least have a ring and at least have 1 pi bond to make it aromatic. And we'll see how that works. Contains carbon, hydrogen, and some kind of halogen. And also here in the hint, I'm giving you some of the ratios between different nature abundance, like chlorine 35 to chlorine 37, that's like 1:3. And bromine 39 and bromine 81 is about 1:1 ratio. So by just reading the top sentence, you're already getting some of the information. You're like, okay, so we have an organic molecule, carbon, hydrogen, bromine. Okay, that's something to keep in mind. And next up, let's focusing on the mass spectrum first. You know, my printer is not working properly. And just remember, just keep in mind to print out your notes for the final exam. Whenever I have chance, I want to remind you on that. Okay. Now, looking at these information, what we have mass spectrum. And the mass spectrum tells us information like molecular mass of your molecule and has a base peak. Okay, it tells you information about how your molecule fragments into smaller pieces. You have IR spectrum that tells you information about functional group. But in this molecule, we don't have an oxygen, so our IR is less informative in that regard. And then we have our carbon NMR that's showing up to be 5 peaks, 5 singlet, showing we have 5 different types of carbon atom. And we have our proton NMR, also with a hint of these chemical shifts on naphthalene. So these are the information we have. And now our goal is to try to use all this information to get to derive what the molecule looks like. So let's get started. We'll first look at the mass spectrum. So that's why I'm zooming out on the mass spectrum. So what are the information we have here? Let's see. So from the mass spectrum, one of the key information we can get is the molecular mass, or what is the MZ of this compound, M plus dot. All right, so some of you were asking where this comes from. So this means we start from a neutral molecule. In the mass spectrometry, what we do is we shoot that neutral molecule with a beam of electron, and we knock off 1 electron from that molecule to form a cation radical and 2 electrons. All right, so this is just a quick review in what that molecular cation looks like. Now, this molecular cation, the only difference between it and the molecule itself is 1 electron, and an electron doesn't contribute to your molecular mass that much. So what we know is the molecular mass of my smiley face is, well, we have 3 peaks here, 284, 286, and 288. And their ratio is about 1 to 2 to 1. Now this is peculiar because we know it has halogens, but how come we have 3 peaks for my molecular iron? Right, if you think about it, if we only have 1 of these halogen, like 1 chlorine, you would expect your molecular iron to have a 1 to 3 size of the peak on your molecular iron. If you have 1 bromine, you would expect a 1 to 1 ratio of your molecular iron. Anyone want to take a guess? Yes.
There's a mix of bromine and chlorine.
That's a possibility. That's a possibility, but we only have 3 peaks, right? If you have a mix of bromine and chlorine, you would expect 4 peaks, right? Because each of the element has 2 different natural abundant, right? So AB, AB, right? Depending on how you mix it up.
Will the 2035 and 3080 have the same molecular weight as 4037?
That's true. That's also true. So, but nevertheless, what we're proposing here is we're having a mixture. So we have 2 different isotopes. We have 2 halogens in this molecule. Now, whether it's chlorine or bromine, that depends on the ratio here. So your chlorine has a 1:3 ratio. Your bromine has a 1:1 ratio. So let's just say you have 1 bromine and 1 chlorine, and let's see what that looks like. So if we have 1 bromine and 1 chlorine, we would have 35 chlorine with 79 bromine, 37 chlorine with 79 bromine, 35 chlorine with 81 bromine, and 37 chlorine with 81 bromine. And if we're looking at these ratio here, now your chlorine 35 and chlorine 37 is a 1:3 ratio. So this adds up to be 35, 37. So these 2 will have a 1:3 ratio, and these 2 will have a 1:3 ratio. And it gets more complicated than that. Let's see. We have 79 plus 35, that's 114. This is 116, this is 116, 118. Now, if it is a 1:3 ratio, 1:3 ratio, so we're talking about 2 divided by, so let's say this one is 1, and this one is 3. This one is 1. Wait, 35 is 1, sorry. 3. So that's our ratio here. So in total, we're looking at 1 divided by 7. And this one, taking together, is 6, well, 1 divided by 8, sorry. 6 divided by 8 and 1 divided by 8. So the difference between our 114, 116, 118, or in this case, a 284, 286, 288, would be a 1:6:1 ratio, right? So that's obviously not correct. So it's not bromine chlorine. And chlorine will have the same problem. If you do that calculation, it does not give you the 1:2:1 ratio. Now the reality here is, well, the only choice we have left is probably our bromine. So what we have is 7, let me just keep it here actually, and copy it down. Now if we imagine we're doing the bromine, then what we have is 79 bromine, 81 bromine, 79 bromine, 79, 79. We have 81, 81, 81, 79. Right, so in this case, now we look at the ratio here. Because my bromine is a 1:1:1 ratio, now each of them will have a 1:1:1 ratio. Right, so your bromine 79 and bromine 81 are like 1:1 ratio. So now let's look at these percentage. The 79 gives you 158. 79-81 gives you 160. 81 gives you 162. 81-79 gives you 150. Wait, did I do that wrong? Yes. Wait, no. Sorry, this one is 160. All right, and now you have one combination, that's 158, one combination, that's 162, and 2 combination, that is 160. So the bromine gives you that nice distribution of the 1:2:1 ratio. 1, 1, and, well, times 2. So that's where that 1 to 2 to 1 ratio comes from. And this explains why we expect 2 bromine atoms in our molecule. All right? So from here, what we derive is our molecule contains 2 bromine. Yes?
So I think I had the right thought process. I forgot that the isotopes were counted, so
Right.
you're doing 4 instead of, because I was just thinking chlorine and
No, but that's a good lead, right? You're looking at that distribution, and when you have like more than 2 peaks on your molecular iron, just think about it. Where that more than 2 peaks come from? It's a combination of different isotopes together. All right, so that's our first step. Now, by doing this, what we can derive is we find out that our molecule contains 2 bromine somewhere. So we know this equals to 2 bromine atom. I'm just going to write on the, wait, I shouldn't, because I need to use that for my lecture too. Okay, so, all right, so nevertheless, so now we have that. We know that our molecule contains 2 bromine elements. What else information do we have in our mass spectrum? Now we see there is a base peak at 126. So what does a base peak in your mass spectrometry looks like? So the base peak in your mass spectrum tells you how your molecule break down into fragments. So that base peak is hinting, hey, we're forming some kind of stable cationic fragment that has molecular weight of precisely 126. So this 126, precisely 126, is a little bit peculiar. So let me copy that down. All right, so our base peak is 126. And this 126 does not have any of those isotopic effects. So that means it's likely we lost both of our bromine atoms and end up having our 126 peak. All right, so with me so far, we're talking about the isotope effect. And we have the isotope effect when you have isotopes of similar natural abundance, like in this case, bromine. So that's why we show the isotopic effects with you, right? I'll be right with you. And if we look at the base peak, it doesn't have any isotope. So that means our bromine atoms are being lost in the process of fragmentation. So how to rationalize that 126? Now we can look at our molecular mass, right? So our 286 is our molecular mass. So 286 minus, well, let's just say that 286 is corresponding to the peak of bromine 79 and bromine 81. Remember, that's the largest peak. And what does that tell me? 286 minus 160, I got my 126. So my 126 only contains carbon and hydrogen. Right, so that's the fragment cation that's being formed after dissociation of the 2 bromine atoms from this mysterious molecule. Now we can get even more information by looking at the molecular mass of this fragment 126. It only contains carbon and hydrogen, so we can easily derive what's the ratio between my carbon atom and between my hydrogen atom and calculate for the degree of unsaturation. Right, remember in our beginning, we were saying this molecule is an aromatic compound, so the degree of unsaturation is at least 2. So let's think about this 126 and what's in there. So now imagine we have 2 different ways that make it reasonable. I mean, obviously you can't have only 1 carbon and then 114 hydrogens on there, right? So there's only 2 reasonable ways to put that 126. Either we have, let's say, 9 carbon atoms. So that 9 carbon atoms gives you 126 minus 12 times 9, which is 126 minus 108. That gives you 18 hydrogens. So this 18 hydrogens is hinting our degree of unsaturation. And also remember, we have 2 bromines around, right? And those 2 bromine counts as hydrogen when you're calculating degree of unsaturation. So here, this 18 hydrogen is assuming we have 0 degree of unsaturation. So that's not correct. You can't have 0 degree of unsaturation because our molecule is aromatic. So this is not right because of my molecule is aromatic. And what about 10 carbons? So that's 126 minus 12 times 10. That gives me 6. Or the other way to put it is we have C10, H6, bromine 2. So what's the degree of unsaturation here? It's 10 times 2 plus 2. So that's our baseline, minus 6 minus 2 divided by 2. So that's 22 minus 8. We have 7 degree of unsaturation. Now, in these 2 possibilities, the only one that is correct is our 10 carbon atom one. So by only looking at the mass spectrum, now we know the molecular formula of this mysterious molecule. All right, so we do that by first work out what are the isotopes, what are the halogen in this molecule, and then we work out what's the potential degree of unsaturation in these candidates. Right, we know it's aromatic, so well, we have some degree of unsaturation, and that's how we get the molecular formula here. Yes? No, you can pick 8, and then you'll figure out it's not right. So if you think about it, let's say 126 minus 12 times 8. What does that give me? This molecule only have right now. This 126 only have carbon and hydrogen, right? So 8 times 12, that's 96. 126 minus 96, that's, well, 30 hydrogen. So there's no molecule that can have only 8 carbon and 30 hydrogens on there. So it's just not correct. So, I mean, there's a limit we can do it, but this is one of the ways that's fast and easy to find out. Just take a guess what it looks like. Yeah.
Why did you do like 286 instead of 288?
You can do 288, but then for 288, you need to minus 81 and then minus 81. It's the same. Yes? Well, the 2 halogen comes from this analysis. We know we have 3 peaks. We have 3 molecular ions, right? So these 3 molecular ions and their distribution is peculiar. It tells me like we have halogen atoms in there, and we have more than 1 halogen. Because if we have only 1 bromine in this molecule, our molecular ion would be a 1-to-1 ratio. But now we have 2 bromine elements, and because of the combination and also their 1-to-1 ratio in their natural abundance, we derived our 1-to-1 ratio and identified our halogens are 2 bromine atoms. Okay, with me so far? We don't just jump in to say it's bromine. It's just because the question is telling you it's either chlorine or bromine. And what's the combination there? And the combination is hiding in the ratio between that natural abundance. Yes? This one? This one? This one's just telling you because your bromine is 1-to-1 ratio, then each of it would have like 1/4 possibility. That's why I put 1-to-1 ratio there. Okay, with me so far? So by doing the analysis of the mass spectrum, we can get lots of information about the molecular structure. Like the question here is, what are the atoms in my molecule? How many carbon atoms are there? How many hydrogen atoms are there? And now we're ready to use other spectroscopy to get their molecular structure, or what's their connectivity between my 10 carbon atom, 6 hydrogen atom, and 2 bromine atom. So, ready to keep going? No, the IR here is not as informative as it normally be, especially in the case when we have an oxygen in there. So the IR here didn't tell us too much information. Well, it tells us we don't have a carbonyl, we don't have an OH, we don't have an NH, but we sort of know it already from the mass spectrum. So the IR here is acting as a quick supportive to what we already find out. But nevertheless, we get lots of information by looking at the NMR. So let's copy paste down our molecular formula here. Right, so this is the molecular formula we worked out by solving the mass spec. How do we use it? Now, how do we use my carbon-13 NMR and my proton NMR together to solve for the structure here? Looking at my carbon NMR, we're saying, hey, we only have 5 peaks in this molecule. 5 peaks, and we have 10 carbon atoms. So this tells us we have some kind of symmetry that gives you that 5 peaks in your carbon NMR. Now in the proton NMR, we're giving you lots of more information by looking at the hint. All right, so if we look at the hint here, this is a naphthalene molecule. Let's think, how many degrees of saturation did we talk our molecule have? Right, so how many degrees of saturation in the hint we have? 7, so it sort of gives you the skeleton. So this is hard, okay, so mixed spec is really hard. I'm never gonna just throw it to you without giving you necessary information, like if it's needed, we'll give you information in the hint. So this is actually telling you, maybe this is a skeleton. Let's just start by using this skeleton and see where to put my bromine atom, and can we rationalize the position of my peaks after we put in the bromine atom. So let me just draw in my naphthalene here. And now my naphthalene has, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And our carbon-13 NMR has 5 peaks. So somehow we're dividing our naphthalene molecule into 2 different sections, so they're chemically equivalent to each other. So my bromine must be put in relatively, say, symmetric positions, right? So you can rule out some of the possibility, like this one. This one is probably not right because it does not have any symmetry, and in your carbon NMR, you would expect much more peaks if we put the bromine this way. So carbon NMR is telling us information about symmetry. And now let's look at our proton NMR. And look at our proton NMR, we only have 3 different types of hydrogen in this molecule. Only 3. 1 singlet, 1 doublet, and, well, another doublet. They're all pretty deshielded. Well, they're aromatic hydrogens, so it's sort of expected to be deshielded. So we have these relationships to go. And I'm gonna pause here so you can think about it. I'm just gonna pause for 2 minutes and I'll leave you to think about it. And we have the hint here for the relative position. And while you're working on it, I'm just going to write down some of the notes I find when reading the proton NMR. We have 1. Singlet at 8.6 ppm. And this one is most deshielded. And because it's most deshielded, maybe it's close to our halogen. Then we have 2 doublets, 1 doublet at, let's say, 7.2. And 1 doublet at about 7.8. And also in here, like keep in mind, these peaks are 1:1:1 ratio. We have a total of 6 hydrogens. Now they're 1:1:1 ratio. This is also supporting our molecule have a plane of symmetry in there. Okay, so now let me just put some number here. 1, 2, 3, well, 4, 5, 6, 7, 8. All right, so how to get started? Let's just say, let's do a quick vote. I mean, there's no point associated to it, but let's do a quick vote. Now, let's comparing, if I have a hydrogen here, and I have a hydrogen here, is my hydrogen 3 or hydrogen 4 more shielded or have a smaller ppm? So that's given in this kind of information. Between hydrogen 3 and hydrogen 4, which one of them is more shielded? 4, right? So now if we're taking a guess, we definitely know this green peak is not my 2, 3, 6, 7. It must be my 4, 5 or 1, 8. Or it doesn't matter because it can be symmetric. So that boils down to my 2 other peaks, the blue one and also the red one. Now the blue one is the most de-shielded. So chances are this is either my 2, 3, 6, 7, one of that. And also it gives out more information. First of all, it says it is a singlet. Now it is a singlet because means it doesn't have any neighboring hydrogens around it. And also it is more de-shielded, means this blue one is more close to your bromine atom. And the other point of view we have, at this more shielded one, we only have a 1:1:1 ratio, right? We only have 2 hydrogens that are more de-shielded, are my green hydrogen. So what are the possibilities? The chances are we can put our bromine at either 1,8 or 4,5 position. It doesn't matter because this one is a very symmetric molecule. After we put the bromine, by doing that analysis, we know that these hydrogens are directly next to the carbon with the bromine. And are they singlets? Now, if we look at this carbon doesn't have any hydrogen, this carbon doesn't have any hydrogen. And indeed, these 2 blue ones are my singlet hydrogen. And what about the red one? The red one is, well, the internal position. These are having a more de-shielded because of the ring current. We didn't cover, but it's in the hint. So these are my internal hydrogen. And 4, 5, we have our green hydrogen. All right. Now, does my molecule have a plane of symmetry? Obviously we do, it's in the middle. And if you count the type of carbon atoms, 1, 2, 3, 4, 5, that's the 5 carbon atoms we see in our carbon-13 NMR. Yes? No, that doesn't matter. You can be down on that side, it's the same. How are we feeling about this kind of question? It's hard, but I mean, this is one of the fun part of organic chemistry is we don't know anything about the molecule, but we have small pieces of information. And what we do as organic chemists is we're putting those information together to solve for what that molecule looks like. All right, let's do one more example, and you probably will do one of the this kind of example in your next week's discussion session. And I promise you, you'll have one of these problems on your final exam. It's inevitable. Okay. Now, example number 2. We have a mysterious compound. Now it's a sad face. Maybe I should put a smiley face at the end. Now, this mysterious compound contains carbon, hydrogen, and oxygen. So in this molecule, this one has a relatively small molecular weight of only 102. And then we have a base peak at 43. And also, there's no peak observed at about 84. Okay. And then we have our IR spectrum. Now, the IR spectrum, in this example, becomes more informative. We have our iconic carbonyl peak on the IR spectrum. So it's telling me that, well, my molecule has a CO double bond. And at the same time, we do not have the broad peak. Remember, we see those broad peak around 3,000 for OH, NH, SH. So any of those stretchings that can involve in hydrogen bonding with the solvent. We do not see any broad peak. So this molecule does not have a OH in it. Also, what we have in our carbon-13 NMR, this one, I should have just tell you, this one has 4 peaks. This one is not very obvious. Let me just write it down. And keep going. We have our hydrogen NMR that's, well, let's save it until we have more information about what my molecule looks like. Okay, ready to get started? Okay, let's look at the mass spectrum first. Again, what we're trying to get from my mass spectrum is trying to derive or deduct what my molecular formula looks like. So let me copy paste this information down. Now, this molecule has a molecular cation of 102. So the molecular weight of this molecule is about 102. It also tells you information about a base peak at around 43. So when we say that it's a base peak, what we're hinting, it is a carbocation. It is a carbon-centered cation that is relatively stable. So it can't be a primary carbocation. It must be some kind of at least secondary carbocation, so it is stable. And then there's no peak at the molecular weight around 84. So using this information, we can get 2 pieces of information. One, there's no peak at 84. What does that 84 mean? So 102 minus 84, that's 18. Right, so that's the molecular weight of water. And in our class, we were talking about dehydration of alcohol in mass spectrometry. So this is an example that, well, there's no dehydration happening. So this one, we have no OH or alcohol. And this piece of information is also consistent in what we observed in the IR spectrum. Now, the second piece of information is coming in this 43. So 43 or like 15, and these are the numbers that after looking at multiple mass spectrum, you'll get an idea. So what happened is in this 43, this one is 12 times 3 plus 7, or 36 plus 7. Or looking at our 43, it's a relatively small number, so it's easier to derive what's the nature of this carbocation. This is a carbocation of 3 carbon, 7 hydrogen. Right, so what that tells us is this molecule, this is an alkyl carbocation. It doesn't have any degree of unsaturation, and we want it to be relatively stable. So what that tell me? It's likely to be an isopropyl wall. And this is about as far as we can go. It's, we don't have too much information in here, and that's it. So far what we know in this molecule. By looking at the mass spectrum, we know it has an isopropyl group, right? An isopropyl group is a carbon with CH3 that's binded to something like a question mark. So that's from our mass spectrum. That's coming from the mass peak, base peak at 43. Now the other piece of information is we know it has a carbonyl group that's not a ester. It's the carbonyl group that is not a carboxylic acid. So what we have is a carbon, oxygen, and that binds to some mysterious groups. Okay? And now let's move on to look at our NMR spectrum. So in here, what we have is in our carbon NMR, we have a total of 4 peaks. So what does that 4 peaks tell us? Well, we have these two are definitely equivalent to each other. That gives me 1. This one is a CH, by the way. This one is our second type of carbon atom. So that's our 2. My carbonyl carbon is a 3. And then, well, you have 2 question marks, and one of them must contain at least a carbon atom. So that's in the carbon NMR. So keep that in mind, right? Now, so far, we have 3 different types of carbon, but we have 1 more carbon atom we need to solve for. Now, let's look at our proton NMR then. So my proton NMR is quite interesting, if you may. Now, this doublet and the heptat are pretty corresponding to what we already know, right? So this doublet and the heptat is corresponding to my isopropyl group. So this green one is our heptat, because it has 6 neighboring hydrogens. And then the CH3, these have the ratio of 1 to 6, right? So the 1 to 6 ratio is clearly demonstrating this 1 to 6 come from my isopropyl group. So the red one is our doublet at about, 1.2. So that's matched up. But at the same time, in order for my green one, or this heptat, to be a heptat, what it means is this one does not have any neighboring hydrogen anymore. It must have only something that doesn't have any hydrogen on there. What is the carbon with no hydrogen on it? Right? That looks right. So we can make that connectivity there. It's not hard, right? It's just like, look at it, it's like, right, that's a heptat. We already have 6 neighbors. I don't want any additional neighbors. And here we have a carbonyl carbon that doesn't have any hydrogen on it. So we can make that connectivity. So now what we have CH. On that CH, we have CH3, that's connecting to a carbonyl group. That's connecting to something. And that's something, well, we have a singlet with integration of 3. So is that methyl group? Sounds right. It's a singlet, doesn't have any neighbor with 3 hydrogens on it. Now, is this our final answer? Let's calculate the molecular mass here, and just to double check, right? So we didn't use our molecular mass information. We didn't use our MZ information there. So let's calculate our molecular mass and double check to make sure we get that correct. So what's in there? We have a total of 1, 2, 3, 4, 5. Hydrogens, 3, 4, 10. And oxygen. And if we do that calculation, you have 5 times 12 plus 10 plus 16, and that's only 86. And what is the difference? Well, 102 minus 86, that's where that 102 is. 102 minus 86, that gives you 16. So we're missing an oxygen. All right, now where to put that oxygen? That goes down again. We know that this group must be a singlet. So it is a singlet, and also this one is a little bit more deshielded comparing to the doublet group, which are my terminal isopropyl CH3 groups. So it's hinting it's closer to either electron withdrawing group or a oxygen. So we can put in our oxygen here. Or our final answer of this molecule is like this. Wait, let me see. Actually, no, I was thinking it the other way. The other way might also work, because my heptide is also deshielded. So if you put it like this, that also works. So, yeah, so you can have 2 answers, and you need to solve it later on. But nevertheless, that's the end of this kind of problem. How are we feeling about it? Yeah, this is the kind of problem. There's no trick. It's just like try it out. And again, when you're practicing on this kind of problem, just keep in mind, do not look at the answer before you actually solved it. Because after you see the answer, you'll be like, this is obvious. I should have seen it. But it doesn't work this way, okay? All right, good luck.